So in this video, I'll be going over practice exam 3, talking about things that you should include in your setup and things that I'll be taking off points for if they're not in there. So I'm going to start off by doing that. So things I'll be looking for in the setup of your problem. So as always, you're going to need a coordinate system. That doesn't change, and again, it's not going to change for the rest of this course. That's the first thing that you should do. You draw your picture, define your coordinate system. That should be pretty much second nature at this point. The second, now for torques, you'll need to choose a positive rotation direction. So what do I mean by that? Well, we've been choosing counterclockwise. That's a terrible arrow. We've been choosing counterclockwise CCW to be the positive direction. It doesn't matter. You can choose clockwise to be the positive direction. It really doesn't matter. It dictates what sign your torque is, depending on what the torque will cause the object to do, which way it will cause it to rotate. So if the torque causes a rotation in the counterclockwise direction, then it will be a positive torque. So this needs to be included. Everybody did fairly well with that. There were some spots where it was missing out of people, but it wasn't a frequent miss from people. So just include that when you draw your coordinate system. You can just stick this right in the middle up here, like the arrow I've just drawn, and that'll be fine. So don't forget that. And then 3, for energy problems, you need to define where your gravitational potential energy is equal to 0. You can also just choose the H equals 0 line, and that will suffice as well. You can label that line either as gravitational potential energy 0, like I have here at the start, or you can have it as the H equals 0 line, and I'll know what you're talking about. But that needs to be included anytime you're dealing with gravitational potential energy. You need to show me where your 0 point is, because that value is based off of this 0 point. So those are the 3 main things that I'm going to be looking for. In addition to the normal diagrams, free body diagrams, rigid free body diagrams, motion diagrams, all of the stuff that we've been doing. But these specifically are the easy points. You're talking a coordinate system and a PEG, or the potential energy of gravitational potential energy 0 point. That's going to be 2 to 3 points. So if you don't have those, then you're already starting with a 17, 18 out of 20. You're starting with a 90 or an 85 just for missing those. So make sure you have them. They're important because they dictate the signs and the magnitudes of certain values. So you have to have them to be able to accurately solve a problem. So if you have questions about that, just reach out, let me know. I don't want it to be any kind of surprise when if I take off points for that. I want to be upfront as possible. So if you have a question, let me know. So getting started, here we have question 1. So question 1 is dealing with 2 cars that are coming towards each other. they have certain velocities and certain masses, and then they collide, and they have different velocities after the collision. And so this is just a simple, not a simple, I don't want to use that word. This is a standard collision problem where you'll use conservation of momentum. So we've done this a ton of times. So this is something you should be familiar with doing, should be able to handle this type of problem. We're given the initial velocities of each cart, and then you're given one of the cart's final velocities, and you're asked to solve for the velocity of the unknown, or you're asked to solve for the unknown velocity of one of the carts. So you'll just apply the conservation of momentum equation that we have right here and solve for the unknown velocity. Again, defining your coordinate system, especially in conservation of momentum problems or collision problems, the direction matters. That was a spot where some people messed up on, because it dictates what the sign of the velocity is going to be. So if your signs aren't right, then your conservation of energy equation, what I've got underlined right here, that's going to be way off. So make sure you define your coordinate system so you can choose the signs of your velocities accordingly. The second question asks the impulse experienced by child 1. So that's the cart 1. Impulse, remember impulse, which is J, is equal to the change in momentum. So M, final velocity minus the initial velocity. So the key here is that this is the change in momentum of a certain system. So since we're wondering what the impulse is, or the change in momentum of the child 1, or the first car, you would want to find the change in momentum of the first car. So don't mix and match these velocities, you know, the velocity of the second child or the second car with the first one. You want to stay consistent that this is the final velocity of the first one minus the initial velocity of the first one. Stay consistent. You know, there's a lot of velocities floating around in these kind of problems, so this is something that could be a potential trip up spot. Then we have the average force experienced by the child if the collision occurs over 0.15 seconds. And now you use the relationship of the change in momentum, or the impulse, and relating it to a force applied over a certain time. Because remember, the impulse is just a force applied over a certain time. So impulse is also equal to a force, average force, over a certain time interval. And remember, that force causes a change in momentum. And how drastic of a change is dictated by the size of that force and the time that force is applied. Think back to the lab with the egg drop. The change in momentum is the same for every single one when dropped from a certain height. But the egg breaks in certain scenarios and doesn't break in certain scenarios because of the force and the time that force is acting. So then you just use what you found in the second part, and you use it to determine what the average force is. This is a large force. I mean, this is why This is why collisions are bad, basically. This is why you want to have seatbelts on, because there's a large force acting on you. And if there's nothing to stop you, then that large force is what sends you flying through the windshield. In this case, it's bumper cars, but this is why bumper cars aren't supposed to be going very fast. This is why they have that rubber bumper up on the front to kind of extend the collision time, because this is a very large force. And this is the force that it's acting on your body. This is acting on your brain. So this is why there's those safety features with those things. So moving on to the second problem, this is going to be switching gears. This isn't a collision problem. This is something else. So we have a family situation where we have a door and it keeps hitting the wall. So there's nothing stopping it from hitting the wall. So you may have seen door stoppers before where they have a coil here and then they're attached to this like rubber bumper. It kind of looks like that. And you know, there's your door or part of your door. And so it stops the door from hitting the wall. You may have seen those. So that is what this problem is centered around. So it's centered around figuring out how stiff that spring needs to be given the requirements that the family wants. So if you have one of these in your house, go check it out and try and push the spring in and figure out how much force you need to be able to push it in. So my guess is, if yours is like mine, it's very difficult to push it in. And the reason why is that you don't want it to be a very loose spring, a very soft spring. Because if a door's moving quickly, then it's not going to be able to take on all of that energy. So it has the potential of hitting the wall. So a stiff spring, so we're expecting something with a very large spring constant, or a K, because it needs to be able to stop the door in a very, very short distance. So what type of problem is this? This is definitely a conservation of energy problem. So what are you going to need to do? Well, you're going to need to figure out where your initial point is and where your final point is. So I've got the initial point as being this door. The final point is the compression of the spring. I still have my coordinate system. I have a potential energy of gravitational potential energy line of 0. Of course, you know, we're not moving up and down, so you don't need to define gravitational potential energy of 0 for this problem, since we're not moving up and down. It's just 0 everywhere. It's just constant, so it really doesn't matter. And then at this point, it's really using our 7-term energy equation and eliminating which ones aren't pertinent to the problem. So we have no friction acting in this problem, so the work done by non-conservative forces is 0. Like I said, it's not moving up and down, so the gravitational potential energy is negligible in this problem. We don't need to worry about it. We're starting off with the door away from the spring, so the spring potential energy is 0. And so we're just left with kinetic energy at the start. We want the spot where the spring stops the door. So the kinetic energy at the end is going to be 0.